Welcome back to the chapter 8, the conservation of energy. So I'm Sorasak Phanphak. I'll give you a lecture through these topics. This is the part of General Physics 101420111 from Kasetsart Universities. So before I already told about the energy of a system, so that we look into the isolate system, try to investigate the potential energy, kinetics energy as well. However, in this case, we're going to expand that point of view. So we will integrate with the knowledge of the non-isolate systems. So what is all about? So the first one, as you can see, this new grass guy swing these pendulums. And what is this showing? It's showing like the energy just initial from the potential energy, and this pendulum can swing, have some speed and reaching initial position. So all of the energy in this system is conserved. So this is in isolated system. However, another case is the guys like apply the force to this lady and get this swing out. So when he applied the force, that means there's some external force exert to her system, which is she set on a swing, have initial potential energy, and with this force, so the speed of this lady when swing out increase. So this is the sample of a non-isolated system. Sorry. So with these two different systems, it means like you have your own yourself individual with the system. From example, the first case, the isolated system is just only the pendulum inside the environment. So there is no additional force involved. So it's like without any change of the energy from the outside. So the other energy in the system is constant or zeros. For another case, there's some energy transfer from other people into the system. So this means the change of energy in the system is equal to the sigma of the transfer energy. This is the transferring energies. So it can be a lot of things involved, not only the force and distance that this guy tried to apply to create work in this part. This is kind of like you have the external work that I already did explain. So now we will focus more in non-isolated system. If you're gonna start talking about whether it's isolate or non-isolate system, you have to reconsider about the environment of the system as well, since this whole thing is a universe of the whole system. If you said in one environment you have the specific system, as I already explained to you, whether it's the basketball with the basket, or individual object, maybe can be a system, like a system 2. So the cat they have its own system. Maybe sit on the wall before jump off the wall. So with this, you can consider this is kind of like an isolated system. But in this case, for non-isolating system, as energy can transfer to each other, cat can maybe jump into the basket and transfer energy to this part. So this is kind of like a non-isolated system. They can transfer energy. So sigma T stand for net or total transfer energies. However, in the environmental one, you have this kind of like a non-isolated system between system 1 and system 2. But however, in environment 2, So this kind of like isolate system, there's no interaction between the environmental one and environmental two, and this guy, he have his own system. So whether it's non-isolate system or isolate system, you can consider the boundaries. So which is this is kind of like boundaries of the system, whether it can interact and have some energy crossing the boundaries, or they may isolate and have no interaction or no energy transfer happen in non-isolate system. So here, this is the key. If you have non-isolate, the chain of energy in the system is all due to the energy that transferred or transferring energy. However, with the isolate system, nothing changes. All energy is conserved. So in this system, delta energy of the system is equal to zeros. That means all is conserved. RVE. Oh, it's conserved. This is R. Sorry. So mean like you do some isolation. You have your own place, and you don't want to share any energy to the other. This is kind of like the mimic of the isolation, as what all we learned of in previous chapter, chapter number 7, in energy of a system. So we will focus more on the transfer of energies, which is it can be in any form, in any kind, for the non-isolate system. The first one is when you try to pushing a box or object, and this object has been pushed and moving along this direction. So the work or external work that's come from the force that we are applying to this block and moving. So this means energy is transferred to the block by the work. For another case, like you have the radio. This is quite the antique type of radio with the alarm. The energy from this system also transfer where the electromechanical wave, the mechanical wave, and this is kind of like the noise or the voices come out due to the air vibration. You transfer the energy in this case as well. In the hot cup of coffee, you also have some energy transfer, which is you have maybe the metal, which is good heat conductivity, heat conductor. So with the conductivity of this, you can touch it and feel about the hot temperature or the heat that transfer from the hot coffee to the spoon. Not only that, the gas that you fuel into your car or engine, that means that fuel can transfer energy to the engine to create the power to drive the car to anywhere you want. Not only did fuel as a matter transfer here into the gas tank, also you can look after like the gas fuel into this part. The electromagnetic wave, like you have some hot air come out. This is kind of like the irradiation of the heat. So this generates from the hot coil. So you apply the energy from electrical energy and apply to this part. That can be in another form of the energy transfer. Finally, but this is not the final one, but this is the final example. It can be inductive between two non-contact system. This is kind of like a wireless charging. So you have electromagnetic wave to get some induction, you transfer energy without contact to the others. So these are just example to name just a few. And you can see the energy transfer here can be anything. It can be chemical, it can be electromagnetic wave, It can be some mechanical wave or noise, for example, or the heat. As you can see, the whole system for non-isolate, we involve with a lot of things. We will learn more in uh, upcoming chapters. But now we're gonna come back and focus on what we learned in the energy of a system from the isolate system, and we're gonna combine to this part. Most of things is all about the mechanical uh, energies, for example, and this is how uh, we try to uh, amplify what we're learning here and gonna expand to cover the whole thing that's happened in the real world. For non-isolate system, again, as I said, what is transferred to the system? It can be work that happen when you try to push the box. It can be the heat that transfer from the cup of the coffee to the system. It can be the mechanical wave when you try to compress the air from the outside. Then you hear a sound, and that energy you record into this microphone, and that energy transfer like a digital into the the digital signal into the PC. This is how the mechanical wave transfer. The mass transfer, for example, like you try to change the fluid, you feel the feel into the tank. That is how the mass transfer and electrical transmission. This is kind of like you plug in the hair dryer or any maybe some kind of electric usage. For example, the electric appliance, fridge, the PC, for example, and electromagnetic radiation is also the wireless charging, as for example. Um, Nonetheless, all these states are involved in this part, as you can see. These are all transfer energies or your sigma T. So with the non-isolate system, you can think about this kind of like a conservative if you look all to cover that part. But if you look at partially, it seems like it's non-conservative. However, we can say this kind of thing is like a conservation of energy equation, since we look after the change of the energy of the system, which is equal to the net transfer energy here. This is the net transfer energy. The reason that I said it's net because the transfer of energy can get out or get in. You can see all these sides can be in and out into our system, since these are boundaries that seal the system you look after from the other environments. As we did in our previous chapter, we can look after the chain of the energy in the system, as you have the total energy from the first event compared to the final one. If you have the sigma E2, which is the final total energy, and you subtract with the initial total energy, what you're gonna get? You're gonna get the work that from the external, or in this case, it's not only the work, it's total transfer energy. So initially we said like only this part as our external work, but now we know we expand it. Not only the external work, but there's also the heat, the transfer from a mechanical wave that which come from the matter transfer, electrical transmission, and also the electromagnetic radiation. So this is how we gonna cover the whole system in our real phenomenon to explain what is happening here. Come back to our isolate system in terms of comparisons, because we expand our boundaries, but because we haven't yet start with the thermodynamics or electromagnetics, So that's why we have to confine our understanding, just focus in the mechanics. So we come back to our isolate system that we did learn. We learned about the kinetics energy, the potential energy, and some kind of internal energy. Internal energy is what energy conserved in that system solely. This is example. When you drop the objects from the height, you know that this object have some potential energy, which is mgh, right? When it drop to the floor, that means you can see on this rate in between the reference or the ground. In this case, it have both potential energy and kinetic energy, since it have some velocity while it's moving. Somehow, when this object drop into the ground, they have no longer have the potential energy. What these two objects or this system have, they have only kinetic energy, which is 1 over 2 mv squared with the terminal velocity, since the initial is from the rest point, is the v0 equal to zeros. This is how we said this is kind of like isolated system in what we look after only the potential energy and some potential energy with the kinetics energy, and finally is with the kinetic energy. As I said before, if we focus only the mechanical energy, that means there is no external work that from the external force done to the system. But now we explain this means there's no transfer energy. So that means the change of energy in the system is zeros. You can use the principle of conservation of energy to state about the sigma of the energy in the final state is equal to the sigma of the energy in the initial state. And your K here is the kinetics energy, U is potential energy, but you will know that the potential energy is not only the gravitational, but also the spring potential energy as well. If they have some spring bound to the floor, you have to reconsider that the spring potential or elastic potential energy is equal to 1 over 2kx squared, since x is the compression or the extension from the original of the spring. Like when you try to extend it from original, or when you try to compress it from the original, this is the x. Now we know about the non-isolated system and the isolated system. Now we're going to combine all these knowledge together and try to explain phenomena that happen through the problem. To summarize what I said, this is in 3 dimensions. So this is in 3 dimensions. As you look after non-isolated system, mechanically, so now we're gonna apply only in the mechanics. The external force that done into this particle along this displacement, the ice displacement, S is like the path that this object moving in a small angle like this. Somehow the displacement is kind of like a path distance that is moving through this. So from this, we know the relation of the external work that apply to the change of the kinetics energy and the change of the potential energy. Somehow, this is lead to this part as we stated before, right? As the K and U, this is from the final one, and this is from the initial one. If you can see the difference of the total energy from the early state to the final state like this, you can somehow observe the work that done by force that exert from the external system. That means this is a kind of things in the non-isolated system. However, if the work that apply to the system is equal to zero, it's become isolated system. Right? And as you can see, you can apply all these force with the direction here in 3 dimensions. It's not only limited to 1 dimension that we did learn. It can be 2 or 3 dimensions as well. This is what I try to summarize for all these things in isolate system. It may look redundant for we keep talking about these again, but I would like you to see the whole big picture of what we try to explain here. The key thing is just whether you have a conservation of energy or not, it depends on the system you're looking after. If you're looking after individual, for example, like a car and moving like this system is isolated. However, if you look into the whole system, if you look after the car moving, this is kind of non-isolated. But if you look after a whole system, for example, this dog as well, moving this car, this is kind of like isolated system. You have the conserve of energy here. But in this case, this is non-isolated system since this dog is pulling this car all the time. So that means they have some external force from this dog and then pull with the distance x. So this is the work from the external. When this car moving, it have velocity so that the represent of the kinetic energy. So how about this one? This guy is floating around, so he may request some work to let him floating like this. So this is how like we see the external work is equal to the potential energy, which is gravitational energy that he have to use for maintain himself off the ground. As you can see, there's nothing that called the completely isolated system or non-isolated system. It depends on how you look into that system. If you look, focus only this man, so this is kind of like isolated system, and the gravitational potential energy is UG, is mgh, if h is the height. For the elastic potential energy, again, if you look only in the part of the spring, it have some elastic potential energy. But if you look the whole system, it may not only the elastic, it also have some kinetics energy as well. So this is how you look into the system. And in this case, you can see the energy transfer between this guy and the spring. And this system, you can see whether you look in isolate or non-isolated system, you have to identify the system that you're looking after carefully. Let's look after the example ones. So as I said, like whether you determine is isolated or non-isolated system, it depends on the boundaries, right? You have to identify the boundaries or the frameworks of the system that you're looking after. Since the first one, A, is what you want to confine the system as you have the ball and the earth as your system. And you would like to determine the speed of the ball at the height from the ground. So you have to determine this v when the ball is above the ground about y. in height. So you determine this system. The ball is released from the rest, right? And then determine what is the speed at this height. So if you look after this system, what you can see, it seems like the system is conserved because the potential energy as is have the initial height as h here, change to some potential energy and the kinetic energy at the y height. So with this case, we said it is the isolated system from this ball Earth system. So with this isolated system, that means it's come with the conservative of energy, right? Sigma E2 equal to sigma E1. So in this case, there's no energy transfer into the system. So the E2 is when it's going to the height y. So it's not only have the potential energy, but also the kinetic energy as well. How about the initial position? There's no kinetic energy since your V0 is equal to 0. That means you have only the potential energy, which is mgh, because it's released from height h here. So this is how you get the information if you look after the system as the isolated system. What you would like to determine, you would like to determine about the y in this case. So you get rid of thing that you don't want him here. So finally, what you get v squared equal to the 2 that multiplied with the gh minus gy or 2gh minus y, which is, if you look after this figure, it's just the change of this position, h dot here. Because if you look after this as the new reference, you can see this is no potential energy. This h dot is h minus y, if you say so. So now you're gonna get for A as your v equal to square root of 2gh minus y in meter per second. This is the system that you're looking after both ball and Earth that have is kind of like isolated system. Now for the B case, what is happened to this system? If you look after the system that you have only ball itself, you have no idea how high of this ball, but what you can see, this ball is being attracted with some force, which is its own weight or the gravitational force pulling this object down, and the distance that this object moving until it's reached the y position is go for this position, right? Is h dot equal to h minus y. So this is happen. This is kind of like you have the ball that has been interact with some force, right? So this is kind of like you have the external work done to the system. So rather than you have the isolated system from the A point of view between the system of ball and Earth, now if you consider only the ball system, this is ball Earth system, right? You will have this as non-isolated system. Since this non-isolated system happened, so you know that rather than you have the conservative of energy in this part, you have the energy of the system chain, which is equal to the net of the transfer energy. Since this case have only the force that pulling this object down with this system, so this is from the external world, which is the mg h dot, which is h minus y. And what happened to the chain of the energy of the system? If the system is only the ball itself, you can see initially there's no velocity, but change to this position is have velocity as a terminal velocity, so that the chain of the energy here, or sigma E2 minus sigma E1, is the chain of kinetics energy, which is 1 over 2 mv squared minus 1 over 2 mv0 squared. Since your initial velocity is 0, so you have no initial kinetics energy in this part. And this is your chain of energy in the system. If your system is only the ball, you have no idea of the potential energy, since you're not compared with the Earth. Like the A asking you about the ball Earth system that you get used to, but now you know just only the ball itself, but you know some force that interact with it. So since you have these two things together, finally you can have the chain of energy in the system that equal to sigma of the energy transfer as the mgh minus y equal to 1 over 2 mv squared. So finally, you can rearrange this term, and you will see your v is equal to square root 2gh minus y in meter per second, right? Whether you look at different type of the system, or isolate or non-isolate system, it can be explained the same phenomenons, but you have to make sure what you look after is cover the whole things. As I said, if you look after both ball and earth, it seems like you have an isolated system. There's no external force involved into this system. But if your system is only the ball, the force, you will feel some force that pulling this object down. The force that interact with this object is kind of like the external force that drag the object down to the earth. But you have no sense of height or the potential energy. So what you feel in that system is just only the kinetics energy. So the chain of the kinetic energy is the total energy transfer, which is in this case is the external work.